also do classical mechanics or ab initio molecular dynamics type of simulation, which actually captures both the dynamics and temperature effect, and solvent effects are also captured explicitly in molecular dynamics simulation. Now, there is another problem with DFT, which is basically this is a single reference theory method. That means you basically take care of one Slater determinant for the electronic configuration of the ions. But for transition metals or lanthanides and actinide, that is not sufficient. So that's why we basically need to use something called wave function-based theory method, which includes multi-reference theory, where instead of taking one electronic configuration of the atom, you basically take an ensemble of all the electronic configuration and take an average. But as expected, that these wave function-based theory methods are much, much expensive than the DFT calculation. And also, these are static calculation at 0 Kelvin. And again, solvations effects and those effects are usually ignored in this type of calculation. That's why in my research, I basically take advantage of all these sorts of methods, and whenever, whichever project fits whichever methods, we just decide accordingly. So in today's talk, I'm going to show you two examples. One is called do defects stock in pyrite iron disulfide, which mostly used periodic DFT calculation. And so let's start there. So why we are even interested in this material, iron disulfide? So this material is a potential solar energy material, but why do we even need another new solar energy material, right? Because currently the 90% of the market is based on crystalline silicon, and which is basically has a photoconversion efficiency of 20%. But problem is you need a very thick layer of silicon to absorb sunlight. Now the other half of the market is based on this type of material like cadmium telluride or copper indium gallium selenide, which requires a 1 micrometer kind of film. But the problem is it's made of either like toxic material like cadmium or scarce material like tellurium, indium, cadmium, and indium is also very expensive. So, for example, this is a picture from US Geological Survey that shows that the abundance of the material is a function of the atomic number. And you see this cadmium, tellurium, these are not very abundant, right, compared to iron and sulfur. So, and then recently there are researches on something like perovskite, right, which contains lead. And the problem there is lead gets easily hydrolyzed. So you don't want a solar panel on top of your roof and then have lead poisoning at your home. So that's why the search for the ideal solar cell material is still ongoing. And in that sense, iron disulfide fits the bill really nicely because it's made of iron and sulfur, which is very earth abundant. And 0.1 micrometer of iron disulfide can actually absorb 90% of the sunlight. It has a suitable band gap of around 1 eV, and it's an indirect band gap semiconductor. So remember, the band gap of silicon is like 1.1 eV, which is also an indirect band gap semiconductor. Now, the theoretical efficiency of iron disulfide is 27%, whereas the crystalline silicon is 32%. And as I said, iron is very cheap. It's only like $0.03 per kilogram compared to the cost of silicon, which is like $1.7 per kilogram. And sulfur is basically free. So, for example, this picture is showing the sulfur pile that is happening as a part of the petrochemical industry waste in Vancouver, Canada. So if we can recycle these sulfurs and make iron disulfide type of materials, we would be actually solving an environmental problem. And iron and sulfur are much less toxic than cadmium or lead kind of material elements, right? Now, this is again a picture of the cost. So we care a lot about cost. So if you look at the cost of iron disulfide raw material compared to its neighboring a competitor, amorphous silicon, this is like 2 orders of magnitude cheaper. So that's why we are very much interested in the iron disulfide solar cell. But the problem is, although it has an expected efficiency of 27%, all the studies that has been done for last 40 years, it never crossed anything beyond 3%. And the main problem there was a doping puzzle. So people were confused whether this is an N-type material or a P-type material. Now, one of the things the confusion was that the crystal structures of the pyrite thin film, pyrite was always N-type, but the thin films of the pyrite were sometimes N-type, sometimes kind of P-type, and there was a lot of confusion with the thin films part. So our experimental collaborators at University of Minnesota basically carefully synthesized both single crystals and thin films and found they are N-type in material. Now the questions they asked us that why this is N-type. Can you explain this from a computational perspective? And the historical suggestion there were some sulfur vacancy kind of defects that is present in this material that is making this iron disulfide N-type semiconductor. So these are the computational questions they asked us that can theory explain the origin of the N-type behavior, and experimentally the material has a band gap of 0.95 eV and then the activation energy of 0.225 eV. That means there is an occupied defect state that is 0.225 eV below the conduction band. Okay, so basically you can think the conduction band as the lowest unoccupied molecular orbital for materials, and valence band is the highest occupied the molecular orbital, like HOMO-LUMO kind of thing in case of materials, and the gap is basically called the band gap in materials. So that was the questions they asked us. And for N-type material, the thing we are looking for is that there should be an occupied defect state, and that has to be near the conduction band. The closer it's to the conduction band, the better N-type material it is. And for P-type materials, we are looking for empty states near the valence band. Okay, so in this case, as I said, it's an N-type material, so you are looking for a occupied defect state and which is near the conduction band. So before talking about the defects and everything, let's just look at the bulk crystal structure of the pyrite and see how we do with our computational tools in terms of predicting the bulk crystal structure properties of the material, right? So in pyrite, it is the iron centers are actually octahedral. So each iron here is connected with 6 sulfur center, and sulfur centers are tetrahedral. So each sulfur is attached with 3 iron center and 1 of the sulfur atom. So this is very important. So I will refer to this sulfur-sulfur bond as sulfur-sulfur dimer in future. Okay. Now from our computed method, we get a band gap of 0.93 eV, which was very close to the experimental band gap of 0.95 eV. And we also found that it's an indirect band gap material. That means the valence band minima is here and the conduction band minima is at a different K point. So that's why it's an indirect band gap material, right? And we also found that the valence band is made of iron T2G orbitals, and then the conduction band is made of sulfur 3p orbitals. So then we started thinking about defects in this material. So what is really a defect? So in iron disulfide, each iron is actually a low spin iron 2, okay? So it's a T2G6 electronic configuration, and each sulfur is a sulfur minus. So when I talk about a sulfur-sulfur dimer, this is a S2 2-. It's more like a par sulfur kind of thing, like a par oxo. It's like a par sulfur dimer, basically, with a 2- charge, and each sulfur has a negative charge. So when we create a vacancy, basically what we do is that we create a supercell of the crystal structure, and then I remove one of the sulfur atom that is shown in white. So once I remove one of the sulfur atom, the iron atom that is shown in red are the neighboring sulfur atom that was directly attached to the vacancy site now. And the sulfur atom shown is green is part of that sulfur-sulfur dimer. Now, once the vacancy is created, sulfur atom will be left as basically 1/8 of the sulfur 8, right? Sulfur 8 is the standard state of sulfur, and that leaves an electron there. So what we are looking is that where is this electron going? Is it going on the iron center, or is it going on the neighboring sulfur atom, or is it getting delocalized all over the crystal structure? So first we computed the band structure and density of state, and we found that there is an occupied defect state. So whenever you see a green line, up to that green line, everything is filled up, okay? And anything above the green line is unoccupied. So here you see the green line is very close to the valence band maxima, which was at 0. and it's occupied, like this state is occupied, and it is zero point 0.8 eV below the conduction band. So that means, although we are getting an occupied defect state by creating one sulfur monovacancy, this state is not making the iron disulfide n-type because it is not close to the conduction band minimum. And this was actually not just us who found it before, but before us, there are multiple groups found this, and they kind of told, okay, iron disulfide is not an n-type material. So we thought, okay, let's try to understand what is happening here in terms of crystal field theory. So as I said, in iron disulfide, each iron is iron 2 and its low spin T2G6. So you have a vacancy site with one electron, and each sulfur is sulfur minus, so that means it's a 3p5. So now the question is whether this electron from the vacancy site will go to the Eg orbital of the iron, or will it go to the sulfur minus and make it a 3p6 electronic configuration. And as expected, we saw that it went to the sulfur 2 minus and make it a closed shell 3p6 electronic configuration, right? It didn't really reduce the iron center. However, then why are we even seeing this new state which is close to the valence band? What is the origin of this state? So as you can see that we created a vacancy, right? So, and initially all the iron centers were octahedral. So now, since we removed one of the sulfur atom, they become like a square pyramidal geometry. So that actually lead to a reorganization of the crystal field. So now the iron centers that were near that vacancy site, they go from octahedral crystal field to the square pyramidal and reorganized the crystal field a little bit. And that was the origin of that defect state, which was very close to the valence band maxima. So then we realized, okay, the monosulfur vacancy will not work. How about disulfur vacancies? And then again, when we looked here, we realized there are 4 possible ways we can create disulfur vacancies. One is basically, if I have 2 isolated sulfur-sulfur monovacancy. One is, since the iron center here is octahedral, we can remove 2 sulfur atom, but in a cis configuration. We can remove 2 sulfur atom in a trans configuration, or we could remove both the sulfur-sulfur atom, which was part of one sulfur-sulfur dimer. Now, one thing you look here, for the 2 sulfur monovacancies, cis and trans vacancy, whenever I am creating the vacancy, there is this neighboring sulfur atom shown in green. However, in this case, for the sulfur-sulfur dimer vacancy, there is no neighboring sulfur atom. So we kind of immediately predicted that, oh, for these 3 cases, whenever there is a neighboring sulfur atom shown in green, the electron from the vacancy side will move to those green sulfur atom and make it a sulfur 2 minus. However, in this case, the electron has to go to the iron center and start reducing the iron atoms because there is no neighboring sulfur atom that is present there. And that might push the electron to the Eg states of the iron and basically move the Fermi energy more close to the conduction band. And that's exactly what happened when we plotted the density of state for these 4 cases. We found that for the 2 monosulfur vacancy, again, for these 3 cases, we get an occupied defect state kind of around 0.8 eV below the conduction band. However, for this sulfur-sulfur dimer vacancy, now this state is 0.55 EV below the conduction band. Remember, the experimental activation energy was 0.23 EV, and we are getting an activation energy of 0.55 EV, so which is still a little bit far off, but we are getting close. And we also found that for sulfur-sulfur dimer vacancy, there is a partial reduction of the iron 2 centers. So that is good. So it's actually showing that sulfur-sulfur dimer vacancies may be one of the possible ways to explain, but we are just talking about the possibilities. Now we don't really know if these things are forming actually, right? So we have to calculate the formation energy of different defects. Now what I'm showing here is that formation energy of different sulfur vacancies as a function of the chemical potential of the sulfur. So if it is sulfur-rich condition, like when you're mixing the experiments, if your like the sample has a lot of sulfur powder, formation of vacancy is actually difficult. That's why it's more positive on the sulfur rich side. But sulfur poor side is when you have less sulfur atoms. That means in your initial synthetic condition, that means you will be incorporating more vacancies in your crystal structure. And that's when it becomes more favorable, right? So one of the things we found is that for monosulfur vacancy, this number is between 2 to 3 eV. Now, for sulfur-sulfur dimer vacancy and the trans-sulfur di vacancy, we found that the formation energies are higher than the monosulfur vacancy, but lower than twice that of sulfur-sulfur mono vacancy. So that means that there is a possibility of defect clustering in this type of material, because the binding energy of the defect, the sulfur-sulfur dimer vacancy and the trans-sulfur di vacancy, is a positive number, okay? Now the question is whether this defect clustering will be thermodynamically governed or a kinetically governed facility, okay? So for thermodynamically these defects to cluster, this number EB has to be greater than the formation enthalpy of the monosulfur vacancy. So you see here the EB is around 0.6 eV, but the formation enthalpy of the monosulfur vacancy is, even at the sulfur poor condition, is around 2 eV. So most likely this defect clustering is not happening thermodynamically. Now, before I go into much more details about this defect clustering, let me talk about a tetra vacancy, because we realize that the sulfur-sulfur dimer and the trans di vacancy are most favorable. So we thought, why don't we create a tetra vacancy where we have two sulfur-sulfur dimer and they are in a trans configuration. And when we did this calculation, for the first time we noticed that changing the supercell size actually changes our result. That means when we are changing the supercell size, we are actually changing the concentration of the defects. So this is the result I'm showing with the 333 supercell, okay, where the defect concentration is around 10 to the power 21 centimeter to the power minus 3, okay. Now, one of the things we notice is that immediately for the tetra vacancy, the Fermi energy moved even closer to the conduction band, and now the activation energy is 0.41 eV. Now, the formation energy of this tetra vacancy is even higher. Total formation energy is higher, like 6.7 to 10 eV. But the interesting thing is that the binding energy is even more positive, that is almost 1.1 eV. That means the tetra vacancy has even more enthalpic gain when they cluster. So that is still, however, this is still actually less than the formation energy of the monosulfur vacancy, which was 2 to 3 eV. So that means we again think that these defects will not cluster thermodynamically. But there is a possibility these defects can actually cluster kinetically. And one of the main criteria for kinetic defect clustering is that this EB has to be greater than 0. And for all the cluster defects, we found that this EV is greater than 0. Now, we also did some diffusion measurements and some diffusion calculation. We actually showed later that these defects are actually forming kinetically, but for the time constraint, I'm not going to go there today. Now, as I said, for the tetra vacancy, for the first time, we noticed there is a result dependence in our calculation as a function of the supercell size. And we found that when we have a smaller supercell, like 2 to 2 supercell, the defect concentration is much higher. And for that case, we see this occupied defect state kind of broadens, and now the gap between the conduction band and this occupied defect state is only 0.1 eV. Now the question is it like really an artifact of our calculation? Because this is a very high defect concentration result. So that means sometimes when you do this periodic boundary type of calculation, there is a self-interaction error of defects. So is it really an artifact, or is it possible to happen? Because we are basically saying that there's an insulator to metal type of transition happening in this material at very high defect concentration. Now, the most important thing here is that at this higher defect concentration, the binding energy of this defect is even more positive. It's almost 1.6 eV. That means at higher defect concentration, defect clustering is even more favored. So we started talking with our experimental colleagues, and what they tried to do is that They tried to change their sulfur to iron loading in their initial synthetic condition and tried to see up to what point they are making high purity crystal structures of pyrite. So they started with almost sulfur to iron ratio of 3 and they went up to 1.6 and beyond that. And they found when the sulfur to iron ratio is 1.6 to 1, they kind of make phase pure iron disulfide. Beyond below 1.6, they started to make FeS crystal structure basically. And one thing they found here is that initially, when they have high sulfur to iron ratio, that means they have less defect, their activation energy is 0.225 eV. However, when the sulfur to iron ratio is higher, they found there is a very low activation energy. It's almost close to 0. So they actually also found that this broadening of the defect band that we are observing at high defect concentration, that is actually possible to happen in this type of material. And this insulated to metal type of transition is indeed possible in this type of material. So basically what we concluded here, that neutral monosulfur vacancy really cannot explain the N-type behavior in this type of material. However, trans-sulfur divacancy and sulfur-sulfur dimer vacancies are most favorable divacancies. Now for sulfur-sulfur dimer vacancy and tetravacancy, the activation energy is 0.55 and 0.41 eV, which is getting very close to the experimental prediction, and we think there might be possibilities of even more complex sulfur vacancies that might be present in this material, and we have to investigate those in future. Now, the main conclusion here was that definitely interacting vacancies were possible for the N-type behavior, and they are actually deep donors. And these defect clustering is actually driven kinetically. So the way I like to think these defects are like human. So like human defects, those in crystals come in seemingly endless variety, many dreary and depressing and few fascinating. So this is a quote from the solid state physics textbook by Ashcroft and Marmin. And as you see here, these defects we proposed are actually kind of like humans. They like to interact with each other. So that's why I started the talk with this title, that the defects really talk in iron disulfide. And we think the defects really talk in iron disulfide semiconductor. So in the second part of my talk, I'm going to talk about discovery of a californium single molecule magnet. So californium and dysprosium, these are like lanthanides and actinides, right? So these are very strongly correlated materials. And for this type of metals, basically, DFT calculations usually don't work. So we have to use something called multi-reference calculation or wave function-based theory calculation. So why we are even interested in something like single molecule magnets, right? So these are actually important for qubits for quantum computing application or quantum memory device kind of application, as well as magnetic refrigeration or spintronic. And when we're talking something like a californium single molecule magnet, this is also very interested in terms of fundamental, because californium is a very toxic element, right? So no one wants to use californium single molecule magnet for a qubit. But we just wanted to see how they behave compared to dysprosium, which is a widely used single molecule magnet. Now, the question is, what are the criteria for a good single molecule magnet, right? So there are basically three criteria. First, it has to have a high magnetic susceptibility. So dysprosium, the magnetic susceptibility is around like 10 to around like the 0 Kelvin, it's around between 10 to 12. Depending on the ligand, it changes a little bit. Now, it also needs to have a high magnetic blocking barrier. So these are basically L plus S states. Like we are basically calculating the barrier between different LS states. And it also needs to be magnetically anisotropic, right? So that means the G tensor values has to be aligned along one of the axes. Now, why we suddenly become interested in a californium magnet, right? So when we looked into the literature, most of the single molecule magnets were either based on this cobalt or dysprosium. And it's pretty much now dominated by dysprosium. So there aren't many actinide single molecule magnets. And there are lot of work going on in this field, but the problem was they are either like very low magnetic susceptibility, and the main problem was the anisotropies are also bad. And for example, if you see, these are some examples of uranium and plutonium magnet. There is no specific anisotropy in one of the specific direction. They are very close to zero in all the direction. And the magnetic relaxation in this type of actinide magnets happens through the ground state. So that means the blocking barrier for actinide magnets are usually zero. Whereas for dysprosium and other magnets, it's much higher. So we were looking for something in the actinide series which has a good magnetic property. So the question we started to look for is it really an issue of 5f electron that makes it a bad magnet, or is it the problem of the electronic configuration, like how many f electrons you have in the metal? So our obvious choice was dysprosium and californium because they are both F9 system, and one is a 4f9 and one is a 5f9. So they are isoelectronics in terms of their valence electrons. So what I found is that using two different methods like CAS-SCF and CAS-PT2, these are like multi-reference method that people use for strongly correlated system, that both dysprosium and californium magnet has very similar magnetic anisotropy. It's close to like 11.5 to 11.9 range at around 0 Kelvin. So that means that in terms of magnetic susceptibility, dysprosium and californium are comparable. Now, we also looked at the magnetic blocking barrier. So the plots we are showing here is that the magnetization between minus mod of L plus A state, like plus minus L plus A states, right? So these are the J coupled states. And what we found here is that for both dysprosium and californium, the magnetic block relaxation happened through the fast excited state. Now, if you look for the californium, the blocking barrier is almost 330 centimeter inverse, whereas for dysprosium, this is 120 centimeter inverse. That means that in case of californium, the blocking barrier is almost thrice that of the dysprosium, which means the californium will be slowly relaxed when it goes to the fast excited state, which is a good property for a single molecule magnet. Now, we also compared the G-tensor values for dysprosium and californium magnet. And as you see, for both the magnets in ground state and fast excited state, the ZZ value is much higher than the ZX and the ZY values. That means both dysprosium and californium has similar magnetic anisotropy. That means californium is actually a good magnet. And compared to other actinide magnet, this has a magnetic susceptibility almost 10 times higher. It has a very significant magnetic blocking barrier and magnetic anisotropy. Now the question is, I'm a theoretician, right? So when I'm coming up with something like a prediction of a californium magnet, no one would really believe me until it's proven experimentally. So our work was done in 2022, published in late 2022. So the question is it really a theoretician's dream, right? Because something like californium magnet doesn't happen every day because it's a very rare element. And if you have like very few micrograms of californium, that means you need to run a lab with a lot of radiological safety equipment, right? And until November 2024, it was actually a theoretician's dream. But then there are two groups in University of Berkeley, Jeff Long's group and Rebecca Abergel's group. They actually made a californium magnet, okay? Although the ligand was different, but they actually first made a californium magnet, which actually has a very similar magnetic susceptibility like we predicted. It's kind of around 10, and it's again almost 10 times higher than any other actinide magnets known. Now, the title of this paper is Slow Magnetic Relaxation in the Californium Magnet, which also we predicted that californium has a higher blocking barrier. That means it will have a slow magnetic relaxation. And indeed, now there are more studies coming up. So this is a theoretical prediction where they changed the ligand basically. So they basically put a californium between two porphyrin-like or phthalocyanin-like system, and they found that it could have even higher blocking barrier. It's now almost 1400 centimeter inverse, which is actually 4 times higher than the ligand we predicted. So this is actually a kind of a new direction we opened about these exotic magnets, and we are now exploring other materials and other elements and try to find new actinide magnets. So with that, I'd like to conclude my talk. So theoretically, we studied the first californium-based single molecule magnet, and we found that they have high magnetic property, very similar magnetic property than with respect to dysprosium, and the magnetic susceptibility is almost 10 times higher. And this is actually the first example of a actinide magnet, which actually has very likely application in terms of some kind of qubit or magnetic separation type of application. So, and the most important thing is that our predictions were actually verified independently by other experimental groups at Berkeley National Lab and UC Berkeley. So with that, I'd like to thank my PhD and postdoc advisors and collaborators, and these are all the funding agencies that funded our work during my PhD and postdoc work. And I just started my independent career this semester, so I'm still building my lab and I'm looking for new collaborations. And so let me know if you guys have any opportunities to collaborate with, and I'll be very happy to help. So with that, I'd like to take any questions.
Thank you, Dr. Roy, for your encouraging speech on the modeling of the materials for the photovoltaics and the single molecular magnet application. So now it's time for the questions, and now this platform is open for question. Let me ask a question. The single molecular magnet, Californium single molecular magnet, is uh, actually be synthesized, or it is a
Yeah, they actually synthesized it now. So my work was prediction, but then the Jack's paper I showed you later, that's a synthesized magnet now.
okay.
Yeah.
What is the special features of this compound?
So one of the thing about this californium like material is that they will go undergo radioactive decay, right?
Yeah.
So that's why you have to be very careful about synthesizing this magnet. But still, some of the isotopes of californium are quite stable. So, but it's the radioactivity is the main challenge compared to uranium or plutonium. That's why most of the focus is on uranium, plutonium, and neptunium. But californium, americium, berkelium, these are like, or curium, these are like actually much harder to deal with in the experimental lab. But since I'm a computational chemist, it's much easier for me to deal these things.
Yeah. Actually, theoretically, prediction is quite easy or by the supercomputer, that, but actually synthesis is very
Yes,
tough.
yes, definitely. That's why, as I said, that no one will believe the prediction until someone makes it.
Okay. Okay, Dr. Anand Mutha, please ask your question, please.
Very unique work, sir. So my question is that is any dopant of the element or any other element with doped one, and in some different ligand, is this work is possible and to have that magnetic compound?
So, are you talking about the first work or the second work?
Yes, sir. First one.
Yeah, the first one is actually so. Yeah, we were first looking at the intrinsic defects. So that's why we looked at the sulfur vacancies, but we also did some work where we doped with all the other transition metals, right? So we basically explained the N-type behavior, and now we want to find a P-type version of iron disulfide, right? So that we can make a P-N homojunction solar cell. So now we are looking for some metals or let's say dope sulfur ions with phosphorus or nitrogen so that we can make it P-type. So that's something we are doing now.
Yeah. Thank you, sir.
Is there any question? Okay. Okay, if there is no question, so again I extend my sincere gratitude to Dr. Demal Roy of Monmouth University for delivering an excellent and enlightening lecture. His lecture was highly informative and intellectually stimulating, providing deep theoretical insight along with the practical perspectives on advanced computational modeling of the materials. The systematic presentation and the clarity with which complex concepts were explained greatly greatly benefited all the participants. The session successfully bridged fundamental principle with cutting edge application in the photovoltaics and the single molecular magnets research, inspiring both students and all the researchers alike. Thank you. On behalf of the organizing committee and all the participants, I convey my heartfelt thanks to Dr. Ray for sharing his expertise, valuable research experience, and for dedicating his time to make the webinar academically enriching and memorable. Thank you once again, sir. Thank you.
Thank you.
Okay, Dr. Demallo, thank you for your quick response for agreeing to come here to our webinar. Thank you. Okay, now we come here to the last part of the today's webinar. That is the vote of thanks. On the behalf of the Department of Chemistry, Bhatter College, Dantan, Autonomous, I consider it is a great honor and privilege to propose the vote of thanks for the international webinar on the current trends in the chemical sciences, CTCS 2025. First and foremost, I express my sincere gratitude to our chief patron, Professor Dr. Giridhari Panda, Principal, Bhatter College, Dantan Autonomous, for his constant encouragement and guidance and wholehearted support, without which this webinar would not be had been possible. I also extend my deep sense of thanks to our President, Professor Dr. Devabroto Mitro, Chairperson, Governing Body, Bhatter College, Danton, for his invaluable support and motivation. I would like to convey my profound appreciation to our distinguished research person, Dr. Demal Roy, Assistant Professor, Monmouth University, USA, and Dr. Chanchal Chakraborty, Assistant Professor, Beats Pilani, Hyderabad, for their enlightening and thought provoking lectures. This expert insight into current and emerging trend in chemical sciences truly enriched the academic experience of all the participants. My heartfelt thanks go to the Department of Chemistry and to the Department of Physics and the Mathematics, along with the IQAC Bhatter College Daton, for their collaborative effort and seamless collaboration in organizing this international webinar. I also sincerely thanks all the participants, all the faculty members, research scholars, and the students from the various institutions for their enthusiastic participation and active interaction, which made the webinar lively and successful. I thank this opportunity to the acknowledge to a dedicated efforts of the organizing committee members, technical team, and the supporting staff, whose behind the scene work ensured the smooth conduct of the webinar. Once again, I thank everyone who contributed directly or indirectly to the success of CTCS 2025. With these words, I conclude my vote of thanks. Thank you all. Now, I am sharing the feedback link to the chat box of this Google Meet platform, and you all participants are requested to fill up this form as early as possible. Please wait for some time. I am sharing the feedback form.